Hi everyone, welcome to my presentation on Rust allocators and memory management. My name is Michael Mullen, and let me jump into the presentation. So what are you going to get out of watching this video? You're going to get a level 2 understanding of memory management on Linux, and you're going to get a greater understanding of the pros and cons of various memory allocators that you can use with the Rust programming language. So the TLDR here, for those who just kind of want quick facts right away, is that there's three memory allocators that I've looked at as my time as a Rust programmer. The first one is the standard Linux allocator on Rust, and it's neither fast nor memory efficient compared to the competition. Now, of course, it's still fast and memory efficient, but we're comparing it to the two other allocators that I'm going to talk about. It has a low memory footprint upon initialization of a program. So if you're not using a program that uses a lot of memory, it's a good allocator for you. The next allocator that I've used is called Memalloc, and it's the Microsoft memory allocator. It's very fast in comparison with the other two. It's not much better at memory efficiency versus the standard memory allocator, but it also has a very low initial memory footprint. Right. And the last one that I want to talk about is Gemalloc. Gemalloc is, it has a very high initial memory footprint, but it can be tuned. Gemalloc can be tuned such that it's very, very fast and it's memory efficient for heavy memory usage workloads. Or it can also be tuned to be slow, but very, very, very memory efficient for heavy memory usage workloads. So the rest of the presentation is going to be going into like talking about what I mean by like heavy memory efficiency, the footprints and stuff like that, how fast it is and stuff like that. But if you just wanted the TLDR, there it is. Memalloc and Gemalloc can be very, very fast. The standard memory allocator is standard and it's good enough, but you can do better with Memalloc and Gemalloc. And the rest of the presentation is going to be kind of talking about why I believe that. So what's the agenda for today? I'm going to talk to you about why I care about this topic. I'm then going to go into a bit of a description about what a memory page is. I'll talk about the heap versus the stack. I'll talk about what vert memory is versus RSS, resident set size. I'll talk a little bit about dirty pages, and then I'll go into a little bit more detail about the prominent memory allocators in Rust that I've used. And I'm gonna spend special attention on Gemalloc. So why do I care about this? I am working on a program right now that has a considerable amount of stringification. So strings are being alloced and freed quite often. There's lots of small strings that are being alloced, along with large chunks of memory at the same time. This program is meant to be inserted into a cloud workload. So that means that the memory needs to be tight. I can't use lots and lots of memory, or else other applications inside of a cloud instance will be starved for memory. So while I was working on the program, I ran a benchmark and I saw the RSS memory usage, the resident set size, balloon to 3 gigabytes. But so I ran it through some analysis tools like Heap Track. And if you want to know a little bit more about Heap Track, put a comment in the description down below, and maybe I'll do a presentation on how to use Heap Track. But Heap Track was telling me that I was only using between 50 and 120 megabytes of memory. So I was thinking like, what's going on here? Why is my RSS so high? So I started doing some work on the program and I started optimizing my memory usage and such like that. And I eventually got my RSS down to 260. But still, that's a lot larger than 120 or 50 that Heap Track was telling me. Um, so I need to give you a dark demo here. I'm sorry, but I can't show you the code that I'm running or the program itself running for various reasons that I also can't tell you about. I'm going to give you another demo later on in the presentation that kind of I can show you and do everything with. But I want to kind of highlight the problem that I had and how I solved that problem. So I'm going to do that by just showing you kind of htop while I am running my program and the benchmark at the same time. So I am running htop, and I'm then going to run my application. And I'm going to run my application using the standard allocator. So this is how I was before, after I've optimized things in the code, but before I decided to use a different memory allocator with Rust. All right, so the program's up and going. And for a benchmark, what I use for my benchmark is just to do a Linux kernel compile. So I'm going to start running the Linux kernel compile. And what I want you to start looking for here is the memory usage of this program called ptmal. And what I want you to pay attention to is the resident size. So this is the RSS of the application. And I also want you to observe the CPU usage at the same time. So I'm going to fast forward here. So I'm going to fast forward until the benchmark is over. All right, so the benchmark is over. And as you can see, I'm using about 120, 119 megabytes of memory inside of my residence, inside of the RSS. Let me run this again with the same program, but now I'm using gemalloc tuned specifically to be very conservative with memory. And again, what we want to pay attention to is the RSS and the amount of CPU being used. So again, I will fast forward until the benchmark is done, but pay attention to those values. All right, so the benchmark is now done, and you'll see that the resident set now is around 41, 42 megabytes for the gemalloc version of this application. But while the application was running, I'm not sure if you noticed, but the CPU usage for the gemalloc version was higher than the standard allocator version. And that's because I tuned gemalloc to favor memory at the expense of CPU usage. You can tune gemalloc kind of various different ways, and I'll get into that a little bit later on in the video. But the thing I want to show you is with the standard version, even after the benchmark ended, it was at more than twice as much RSS size than the gemalloc version. So gemalloc is at around 41, 42, and the standard version, the standard allocator version, was at 119, 120 megabytes being used after the benchmark is finished. So what's very important to me here is I don't want to be using that memory without kind of a good reason for it. Because again, this is going to be going into a cloud scenario, and I don't want to be hogging resources. Now, of course, I'm also hogging the CPU during the benchmark test, so there's kind of trade-offs that I need to make. But this is kind of a the most dramatic way I can show that gmalloc is a little bit better than the standard allocator um, for returning memory back to the CPU. So let's get back to the presentation. So let me give you the level 2 version of memory management in Linux. I'm going to be glossing over a lot of stuff, but this is about as much as you need to know as a professional programmer. If you want to get more in depth and kind of get some real understanding, kind of how to optimize memory usage and all that stuff, you can do that. But I'm just going to give you kind of it's more than a level 1, but it's not too much more here. So heap versus the stack. What are they? The stack is where you have your local variables. These are the variables that you use in inside of a single function call or a stack of function calls. The idea is that they get pushed and popped. Variables get pushed and popped onto the stack as the program enters and exits functions. It's limited in size. It's normally tuned to 8 megabytes on Linux, but it will never it never becomes fragmented because it's always either using a variable or not using variable. It either pushes a variable on that's going to be used or it pops it off when the function exits. The heap, on the other hand, is where dynamic memory is allocated. And dynamic memory isn't pushed and popped per function. You kind of dynamically allocate memory in a function, and then your function can leave, and the dynamic memory is still usable when you come through from another function somewhere else. Or it can be used to store larger objects in memory that are larger than that 8 megabyte size. So if you've got, like a big text file that's 10 megabytes in size, you need to start using the heap. So that's when you would use the heap to store that file in memory if you wanted to do such a thing. Basically like that. It's unlimited. The heap is unlimited in size, with the exception that you can't go over how much RAM you have on the system. So if you have 30 gigabytes of RAM on your computer, you of course can't use 33 gigabytes because, like, physical constraints, you can't beat physics. You access the heap by malloc and free. And the problem with the heap, and the problem that I just showed you in the dark demonstration, was that memory becomes fragmented. And that becomes a problem, especially in cloud scenarios, where if you configure a container to limit your amount of memory, Kubernetes or Docker, once you exceed that memory size, will kill your application. If you don't limit your memory, and you're running in a cloud scenario, you're using up resources that other applications want to use. So you're causing problems if you've got fragmented memory and you're not, like, sharing it with others. So what is a memory page? A memory page is what happens when a program requests memory from the OS. The OS won't just give you the exact amount of memory that you want. It will give you a page of memory. So, for example, a program asks for 16 bytes of data. The OS isn't going to give the application 16 bytes of data. It's going to give it a page of memory. Pages are usually 4096 bytes large. So if your application asked for 16 bytes of memory, the OS would say, here's 4096 bytes. Here is a page of memory. Now, the level 2 about this is that your program does not actually ask the OS for memory. What your program does is it asks an allocator for memory. And then the allocator, if it needs to, will ask the OS for memory. So why this is important is your program needs 16 more bytes of data. It will ask the allocator for 16 bytes of data. The allocator in this scenario does not have 16 bytes of data to give it. So it will ask the operating system for memory. the operating system will give the allocator a page of memory, and then the allocator will give the program the 16 bytes. So then your application wants another 16 bytes, and it says, hey, allocator, I would like another 16 bytes. Now, the allocator has 4096 minus 16 bytes. So the allocator has 4080 bytes to use. So it doesn't need to ask the operating system for more memory. It will just say, okay, program, I have more memory to give you. Here is 16 more bytes. So that's what a memory page is. A memory page is kind of the operating system chunks out the memory into these certain sizes of memory that it gives the allocator. And these pages are usually 4096 bytes in size. So when we were looking at htop, you saw that there was vert here and that there was res. So res, also another way of you might see res is RSS. Resident set size. So virtual memory, how is that different from res? Why are these two values different? The virtual memory is the amount of memory the program thinks it can use. So when you do a malloc inside of your C application, but you do not use that memory, you don't write to it, that is virtual memory, and you're taking up space in virtual memory. But this doesn't really impact anything. This isn't like real. It's virtual. It's not real. The RSS, the resident set size, is how much memory your program is actually using at any given point in time. Kinda. Also, there are also two different ways that your allocator can ask the operating system for memory. One way, which is favored by the standard allocator, is through the use of the SBRK system call. And what that does is the heap grows from the bottom up. And the way that it grows, one of the ways that it grows is using the SBRK. So SBRK simply says, I would like to move the heap up. And when your program runs that SBRK, that memory counts towards the RSS. The other way that the allocator can ask for memory is via the mmap system call. So when you run the mmap system call, you say, hey, the allocator says, hey, operating system, I would like 16 megabytes of data. If you do not write into that data, it is only virtual memory until you actually use it. Once you actually use it, then it becomes part of the RSS. I have a quick demo to show that as well. What did I call it? All right, so I've got this demo code here. So this is a plain seek program to kind of demonstrate memory management between RSS, virtual memory, BRK, and mmap. So what this application is going to do is it's going to do one allocation of a certain size, and this is going to be a pointer to characters. It will then, for each of those pointers, it will then allocate another amount of memory. So this is kind of the concept of a multi-dimensional array, except it's not an array. It's heap backed memory. So I'm making a multi-dimensional array with heap memory rather than with the stack. It will then fill up that memory with just A's, and it will then free the memory And there's two different ways that it can free the memory, and I'll talk about those as we're going through it. And then the program exits. So I need to open up another. We can just htop this, and we will look for Dizzy. All right, so let's GCC. Let's do an O3 on this, and then we will run DZY. All right, here. So this is before any of the allocations come through. You can see that the resident set is very low at 800 kilobytes. I'm then going to do all of the allocations, or do the first allocation, and you'll notice that there was no change to the resident set there. I will do all of the individual allocations, and you will notice that in this case, the resident set filled up at the same time as the virtual memory filled up. And that's because in this scenario, we are using BRK to change the heap. I'm then going to fill all the data, and you'll notice that there's no change in the resident set size. And then I will free the data, and you'll notice that the resident set size got a bit lower. And then I'll exit the application. Okay, so to demonstrate kind of the differences here, I'm going to run this, but using gemalloc instead of the standard allocator. And hold on, I've got a cat problem. All right, the cat problem has been addressed. I'm now going to run the DZY through gemalloc, which instead of using BRK, will use mmap. I think I've got this somewhere in my history. If not, we will just... There we go. All right, so I'm going to run this through... I'm going to use gemalloc as the allocator for this program now, and let me just run it. Okay. So you'll notice that the resident set size is a lot larger than with the standard allocator. We're at 9 megabytes in size. This is before doing any of the heap allocation. And then I will allocate all of the individual spots. So now you'll see that the virtual memory here is at nearly 600 megabytes. But the resident set isn't anywhere near that because we haven't written into any of those mmapped allocations. I'm then going to fill the data, and you'll see that the memory is now filled up, and then I will free the data, and you'll notice that the resident set went back down. And exit the program. Okay, now I would like to demonstrate using a backwards deallocation. So what do I mean by that? So in the previous run, I was freeing the memory by freeing 0, then 1, then 2, then 3, then 4, then 5, then 6, up to 500,000. No, up to 1024. Mem amount is 1024 right now. Nope, it's 500,000. Now I'm going to do it backwards. Okay? I'm going to free 500,000, 499, 498, etc., etc. Just make sure that that's, yeah, it's free backward. Okay. So I will run this through the standard allocator this time. And again, we've got our resident set at 800. Do both allocations, and you'll see that it's up to 512. Just the same as before. I will fill it, and nothing will change. And then I will free it. and not very much has changed here. It's still at 500 megabytes, but I freed all of that memory. And then I will exit the program. Now let me run it again through Gem Allocator. All right, it's again at a much higher initial value than before. I will do the allocations, and you'll see that it's the same as the last run where we've got 596 megabytes inside of our virtual memory, but only 28 megs inside of our resident set size. I'll then fill all of the data, and we're back up to 527 megs, and then I will free all the data, and the resident set size goes back down. And then we're done here. So what I just demonstrated is the concept of dirty pages. So dirty pages are memory pages that have become, they've been written into, they are RSS. They've either been written into because they are mem mapped and written, or they are SBRK and they've been raised up. The system break has been raised up. The heap has been raised up. They've been freed, but they've not been given back to the operating system. So I gave you a very contrived example previously, but many applications have this problem where one of the ways to demonstrate this is, let's say that you do a 9.9 megabyte malloc. So in that case, the operating system is going to set aside 10 megabytes of space for you. It's going to set aside 2,560 pages, each of 4096 bytes in size. But you only use 9.9 of it. You then follow up by doing another malloc and write to 64 bytes of data. Your application then frees the 9.9 megabytes, but the 64 megabytes is still used. That means that all of that memory, all of that 9.9 megabytes, that 9.9 megabytes is now dirty, and the allocator cannot give that memory back because you're still using that last 64 bytes of data. So that giant amount of pages that the operating system gave you is still in use by something. It's still in use, like in a very minor amount, but it's still in use. So you can't give it, the allocator can't give it back. So those are what dirty pages are. The good news is that the allocator can reuse dirty pages. So if you came along later and said, I would like 5 megabytes, the allocator would not have to ask the operating system for that memory. It would just have it to use. And then you can go about using it. But of course, the problem is that, like, let's say that you have constraints where you want to be as small a memory footprint as possible at any one point in time. You've got dirty pages and you can't get rid of them. So let's talk a little bit more about Rust allocators. I've looked into 3 different allocators. There are a few more that I haven't kind of played with, but they're out there, and maybe you would like to play with them and comment down below and to telling me how they act in certain situations. But the 3 I've used is the standard system allocator, and on Linux this is provided to you by glibc. And it uses the ptmalloc algorithm, or at least it was initially based on the ptmalloc algorithm. It's grown since then and gotten a little bit better. The standard system allocator on FreeBSD or on Android is gmalloc. And of course, Apple has its own allocator, but I wasn't able to find documentation on what they call it other than libmalloc. The other 2 allocators that I've played with are, of course, gmalloc, and another allocator is called memalloc. Memalloc is the Microsoft's allocator, and I talked about it before in that it's very, very fast. So how do you go about using different allocators in Rust? Well, it's very, very simple. First of all, you just add to your cargo toml the crate which will provide the allocator for you. So in the case of memalloc, it's just memalloc equals whatever version of memalloc you would like to use, or gem allocator equals whatever version you would like to use. And then inside of your main.rs, or whatever the main of your binary application that you are using, you can do the following lines. You can use memalloc : memalloc, and then do a hash global allocator, and then say the static global of type memalloc is memalloc. Now you're using the Microsoft allocator in your program. You can do a similar technique with gem allocator as well. So it's very, very simple to use these. Gem allocator can also do a few more things for you beyond just kind of adding it to your main and adding it to your cargo toml. So first of all, let's talk about gemalloc a little bit. It's formerly Rust's primary allocator. So many years ago in internet time, when Rust shipped the compiler said you are going to use gemalloc. You're not going to be able to choose what allocator you want. You get gemalloc and have fun with it. Since then, they've taken gemalloc out as the only allocator that you can use, and given Rust programmers the ability to use different allocators as they see fit. But they've also introduced the system allocator that whatever your operating system will give you. So gemalloc favors using mmap over brk. And it does this by mmapping arenas, and these arenas can be used to limit fragmentation. So in one of the cases that I've kind of hacked around with, the default seems to be, for me, that there were 130 arenas allocated for me. And that meant that fragmentation isn't going to be so great, because those arenas are kind of going to be limited into how much I'm using them, limited in size and all that sort of kind of. They've got an intelligent algorithm which says, okay, you're allocating this much space. You can put it into here, into this arena, and then when you free it, it's also going to be freed with other things on the thread that you're using at around about the same time. So we might be able to give that memory back to the operating system. Of course, it can be tuned to various different things. So you can tune it to only use one arena if you wanted to. You can tune it to use lots of arenas. You can tune gemalloc to have these arenas cleaned up by a background thread, rather than being cleaned up immediately upon free or alloc. There's various different ways that you can tune it. Please see the documentation on all the different things that you can do. But it means that you can be like exceptionally conservative about how your application is going to be freeing RAM, or it can be incredibly performant for the CPU to just kind of leave all those dirty memory pages lying around to be reused later, because asking the operating system for memory is a context switch, because you're doing a system call. And it means it's going to be slow whenever you ask the operating system for more memory. So yeah, one of the other things that you can do with gemalloc is that you can add profiling stuff into doing gemalloc as well. So it will print out how much memory you're using when you exit the program and things like that. And you do that by compiling your application using this gemalloc _sys_with_malloc_conf. You put in your tunings, and then you cargo build or cargo run your application. So let me give you a better demo here, so I can show you kind of more stuff. So this demo, I've used this application before in previous videos. where I was talking about the efficiency of Rust versus the efficiency of Node. So it's a simple application where we've got an Axum web framework, and I'm only going to be looking at this user's JSON route, and this user's JSON route is just going to query a Postgres SQL database for 75 users and then present that in JSON format to whomever is making the query. Pretty simple application. If you want to learn more, see my previous few videos about this. But yeah, I've compiled this program four different ways. I've compiled it with the standard allocator. I've compiled it with memalloc, and I've compiled it with gem allocator in performance tuning and gem allocator with heavy conservative tuning. So let's run these and let's do an OHA benchmark of each of these programs to see how they kind of work with each other. So let me first run the standard allocator version, and I will do an OHA test, and we will see what kind of results we get. All right, so we were using the standard allocator. We were able to handle 24,075 requests per second. And after the benchmark is over, we can see that we're using 8 megabytes of memory. All right, now I'm going to run with memalloc. And let's run the benchmark again. All right, this time we were able to get 25,573 requests per second, which is a pretty significant boost over the standard allocator. Let's do some math here. So we've got 25,573 divided by 24,075. It's about 6% better. It's about 6% more requests per second that memallocator was able to run over the standard allocator. Now let's run the gemalloc, but in memory conservative mode. So in this case, we got a lot less requests per second. We only got 17,184. And I don't need to do any math to say that that's significantly worse than what we got with the memallocator. Also, let's check out how much RAM we're using at this point in time. We're using about 16 megabytes of memory, which is twice what we had over the standard allocator. So in every way right now, gem allocator is a little bit worse than the standard allocator. And I'll talk about why that is after we finish off our benchmarks. All right, and let's run gem allocator in performance mode. All right, so that's a whole lot better. 25,481. How much was memallocator? So it's about the same as memallocator. They're within variants of each other. I've done this test multiple times before demonstrating it to you, and sometimes gem allocator is faster, sometimes it's a little bit slower, but it's always kind of within variants of memallocator here. However, let's take a look at the memory usage, and you can see that we're using 89 megabytes of memory. So that's a problem. Of course, don't forget that first demonstration on the dark demo that I showed you, where gem allocator allowed us to give back memory to the operating system after we used it. The problem or the benefit of this test is that it doesn't jump around with the memory. It kind of sets the memory and then it kind of stays where it is. And it doesn't use too much more, doesn't use too much less. It kind of gets what it needs and just stays there. However, the performance of gem allocator could have been tuned to be much, much faster, right? That last one was as fast as memalloc. And if I were to use gem allocator even in fast tuning on an application that jumps around with the allocations, where it allocates a lot, frees it, allocates a little bit more, frees some in the middle, frees some at the bottom, frees some at the top, gem allocator would be very good there because it will return that memory to the operating system better than both memalloc or the standard allocator. So what's the conclusion? Well, the conclusion is that you should use gemalloc if you must return memory to the OS and your program is very allocation heavy. It's doing all of those different, like allocate here, allocate there, allocate the other space, free, alloc more, free more, alloc more. It's good in those situations, and it can also be used in performance mode. However, in performance, while it is equal to memalloc, overall it will have a larger overhead if your program is memory stable. So use gemalloc and tune it as you need to if you have a very allocation happy application. But if you have a memory stable application, you should think about using memalloc, which is as performant as gem allocator on its best day, but it doesn't have that huge memory footprint. Let me show you one more time the memallocator memory footprint. So at the end of the test, you can see that it's only using 10 megabytes of memory as opposed to the 89 or 90 that gemalloc was using. Before I go, I would like to show you how you can quickly and easily start playing with these allocators. So if we go back and take a look at the main.source code, you'll see that I've got kind of this area squirreled away for doing the allocator stuff. So if you use memalloc and you give it a name of alloc and do the same with the two other different allocators, just call them all the same thing. You don't have to change this line of code to kind of play around with it. All that you would need to do to start using gemalloc here is comment away memalloc and use gemalloc. Now I don't have to do any other steps here. I'm now going to be using gemalloc. To compile gemalloc and like tune it, what you can do is when you compile up your application, so you see that I've got the cargo build command here. Just give this environment variable and set it to the tunings that you want to do before you give your cargo build incantation. It's as easy as that. Now, if you want to play around with like changing your gemalloc without changing your source code, you'll need to touch your source.main, depending on what you need to do to make sure that there is something that will cause gemalloc to recompile with these configurations. So I hope you have enjoyed the video. I hope you've learned something about Rust allocators, about Linux, about memory management, and I will see you in a next video. Thank you.